All right, in this video we're going to be going through the Fission and Fusion practice worksheet. So we have both fission and fusion. Fission, we are taking a nucleus of an atom. So here's our nucleus, and we're going to bombard it with neutrons. That nucleus is going to then break into two smaller nuclei, and it's also going to release three more neutrons in the process. When it does this, it's releasing energy, and we use that energy in nuclear reactors to generate electricity. Now with fusion, we have the opposite process. With fusion, we have two smaller nuclei, and they come together and are smashed with a tremendous amount of energy, and they combine to form a larger nucleus. So let's take a look at our problems here. Now, in the directions, it does tell you that we can have either fission or fusion, which we just talked about, or nuclear decay, which we covered in our last video. So let's be on the lookout for both. Now, I'm just going to go through my list here and kind of pick out the obvious ones. So for number 2, for example, I see that that's going to be beta decay because we are losing that proton. Losing that proton. And let's see what else. Do I see any others that pop out? Here is beta decay here. The order doesn't matter. So the beta particle can either be listed first or second. Remember, with addition, it doesn't matter if you do 2 plus 3 or 3 plus 2. They both come out to 5. All right, so those look like the obvious ones there. Now let's go ahead and go through, and we're going to have to do a little bit of math to figure out what's what. So for this first one, we are going from 238 to 234. So 238 minus 234 gives us 4. And then 92 and 90 is 2. So I'm going to just write in 4 and 2. And if you look at the periodic table, that gives us helium. And remember, anytime we see helium in the process, that is going to be most likely alpha decay. All right, we already identified this one as beta decay. And same thing with the next one. So we just need to kind of fill in the blanks here. So for the second one, we've got 7 and -1. When we combine those, we get 6. 14 and 0 combines to 14. So this is going to be carbon. We look up atomic number 6 on the periodic table to get that. For the next one here, remember, the left side and the right side needs to balance. So what plus -1 gives us 90? That's going to be 91. And on the periodic table, that is Pa. And our mass numbers need to add up to 234 here. So we are getting nothing from here, so this is going to be 234. Because again, the left side of our reaction and the right side of the reaction need to balance. All right, number 4. Now, number 4, we see that we have a neutron in the reaction, and that neutron is combining with a uranium nucleus. Now, when we see a neutron combining with any kind of a nucleus, that's most likely going to be fission, because that nucleus is being bombarded with that the neutron, and that's what's going to break it up here into our two smaller nuclei. So we need to make sure that everything's balanced. So I've got, let's see, 236 on the left side, and that needs to balance with 146 plus 87 plus something. So let's see, 236 is going to be equal to 236 and 146. Let me grab my calculator. So that's going to be, oops, I put that in wrong. 146 plus 87 is 233. Okay, so the difference between 236 and 233 is going to be 3, and that is going to be the neutrons that are left over. So this is going to be We have neutrons left over. Now, to get 3, I'm going to put a 3 in front of this, because that 3 distributes to the 1, and the 3 also distributes to the 0, but we're more concerned about the mass number balancing. So let me just kind of throw this into my equation here. So we know this has to be 3 because... So when I subtract 233 from both sides, this gives me 3 equals x. Now, the only thing we're going to be adding here, because we know it's fission, is going to be our neutrons. And neutrons have a mass of 1, but we need 3 of them. So again, I'm putting a 3 in front. That 3 distributes to the 1. It also distributes to the 0. But again, we're only concerned with the mass here. All right. Number 5. So number 5, if you look at it here, our mass isn't changing, but the number of protons is. So that right there should tell you that this is going to be beta decay, because the mass is not changing. All the other types of decay, I guess with the exception of gamma decay. So alpha decay, we have a mass number that changes. And then fission and fusion, we have all sorts of mass numbers that are changing. So, if the number of protons goes down, but the mass number stays the same, if the number of protons goes up, but the mass number stays the same, this is going to be beta decay. All right, number 6. So let's take a look at our left side and our right side. So we're looking at 226 and 222. So 226 minus 222 gives us 4. And then 88 and 86 will give us a difference of 2. So you should probably pick up on these patterns by now. 4 and 2 gives us our helium nucleus, which is going to give us alpha decay. Okay, moving on to number 7. We know that this one already is beta decay, so it's just kind of a matter of filling in the blank here. So 18 and 0. So we're going to need 18 on the right side of our equation. And then we've got 9 and negative 1. That is 8. So again, I'm looking at this. I need this to balance out. Sorry, that is not 8. That is actually going to be 10. Because 10 and negative 1 is 9. 10 on the periodic table is neon. And this is going to be beta decay. All right, number 8. So take a look at what's happening in number 8. We have 2 hydrogen atoms, and they're being combined. And let's see, we have a neutron that's being split out. So in this case, when you see 2 small atoms that are being combined to generate something, this is going to be fusion. Okay, so if you look on the left side of the equation, we have a mass of 5. That's the 3 and the 2. And this is going to be equal to x plus 1. The 1 is coming from our neutron over here. So by doing some math here, we discovered that our mass is going to be 4. And then let's see, on the left side of the equation, we have 2. So we've got 1 proton, 1 proton. Here, the neutron has no protons, so this is going to be 2. So this one's kind of confusing because you see the helium here, which sometimes is indicative of alpha decay. But in this case, because we see that we have 2 smaller atoms on the left side, and they're being combined. In this case, it's fusion. So that was kind of a tricky question there. All right, so in this one, I missed this earlier, we have helium on the right side of the equation, or the right side of the reaction. So this is going to be alpha decay, because we're only dealing with 1 term on the left side. Like in the last one, we had 2 different terms, and they were being combined. But since we know there's only 1 term on the left side this time, this is going to be alpha decay. So again, with alpha decay, it's just a matter of balancing everything. We've got 204 and 4. That is going to be 208. And then we have 82 and 2. This is going to be 84. 84 on the periodic table is PO. And like I said earlier, it's alpha decay. All right. Number 10, we have a neutron on the left side of the equation, so most likely this is going to be fission. You also see that we've got 3 neutrons being kicked out, which is also common with fusion. So in this case, it's just a matter of making sure that everything balances. So on the left side of the equation, we've got 90, 143, and, well, this should be 3 times 1. So I'm just going to circle the 3. So let's see, we've got 90 plus 143 plus 3. That 3 comes from the 3 distributing into the 1. And on the other side of the equation, we have 1 plus x. Because, again, we don't know the mass number here. So let me combine terms. 90 and 143 is going to be 133. Sorry, 233. 233 and 3. And then, let's see, x plus 1 equals 236. I feel like I did some math wrong here. Let me check my math. Recording this after school, and I'm tired, so it's very possible that I made a math mistake here. Let's see, 236. Nope, that ends up being right. Maybe my key is wrong. So let's see. X equals 235. Nope, I just can't do basic math. 236 minus 1 is 235. All right, and then I'm going to do the same thing with the number of protons. Again, the number of protons should match up, or should balance on either side. So I've got 238 and 54. It's not 238, that's just 38 and 54. Again, recording this after school, tired. This comes out to 92. Okay, so 92 on the periodic table should be uranium. All right, let's move on to the back side. 2 more problems. Okay, so again, I've got a neutron on the right side, or sorry, neutron on the left side. I've got the 3 neutrons being kicked out on the other side. So we know that this is going to be good old fission. So it's just a matter of making sure everything balances. So let's start with the masses. So I've got 1 and 235. That is 236. And then on the other side, we have 146 and 3 times 1. But don't forget we have our blank. So this is going to be, what, 146 and 3 is 149. Better use my calculator to make sure. So x is going to be 87. So 87 is our mass number. Oops. 87 is our mass number. Okay, and then let's go ahead and let's balance the protons next. I erased our 87. Let me put it back here. Okay, so I've got 0 and 92. That's just going to be 92. And then on the other side of the equation, we have 57 and 0. Of course, our blank, too. So 57 plus x. So when we solve for x, subtract 57 from both sides, x ends up being 35. 35 on the periodic table is good old bromine. All right, moving on to our last problem here. This one is actually the exact same type of problem. So we'll approach it the same way. Let's go ahead and balance our equation. So we've got, let's start with the mass number. This is the exact same thing. This is going to be 236 equals, we don't know, plus 97 plus 2 times 1 is 2. 236 equals x plus 99. X is going to be 137. All right, and let's do the same thing with our protons. So this will be 92 and 0. We'll just leave that as 92. And we don't know because we have a blank, 40 and 0. So x is going to be 52 because we subtract 40 from both sides. And this is TE. All right, let's go ahead and move down to this wonderful word problem. So we know that we're dealing with uranium. 235 is the mass number, so let's write that out. 235. Uranium is number 92 on the periodic table. And let's see, it says it absorbs 1 neutron, so we need that. And it produces, let's see, Sb 125. Sb on the periodic table is 51. a nucleoside, and 4 neutrons. Or sorry, no, SB125, a nuclide and 4 neutrons. So let's see, 4, 1 neutron, okay. And then we got to kind of fill in the blank because it doesn't tell us what the other piece is. So let's approach this the same way we did our last one. We've got, on the left side of our equation, dealing with the mass, we have 1 plus 235, and that's going to balance with 125. 4 times 1 is 4, plus what we don't know. So 236 equals, this is going to be 129 plus x. When we solve for x, we get 107. Do the same thing with the protons. So we've got 0 plus 92 on the left side. Whoops, not plus, this should be equals. And let's see, we've got 51 plus x. X is going to be 41 in this case. 41 on the periodic table is NB. And there we go. Okay. So this one says, explain why nuclear fission reactions produce energy using the equation E equals mc squared. Oh boy, this is a doozy right here. So let's see what we're working with. So we've got uranium-235, we've got barium-141, and then krypton-92. So if you look here, we have a mass of 235 when we start. So initial mass is 235, okay? And then when we look at what's produced here, so produced, we've got a mass of 141, and then we also have a mass of 92. So when I combine these, we get 3, this is 233. So we have a difference in mass here. So we're going from 235 to 233. And that difference in mass is these neutrons right here that are kicked out, that energy. So what we say here is that the initial atom, the uranium-235, has more mass than the daughter atoms. And that's the barium and the krypton. And the difference in mass is converted to energy. And there you go. So in our equation here, E equals mc squared, when we're talking about the energy that's being produced, we're looking at the mass here. So the difference in mass results in more energy being produced in this case. And there you go.